So good morning students. So today in this video we learn about isomerism in transition metal compounds. So the word isomer is derived from the Greek word, that is iso means, so that I think all of you know, is equal or same. Mer means its parts. So what is isomers? Isomers are called as equal parts. So the word was coined in the year 1830 by Swedish chemist, that is Jacob Berzelius. In the year 1830, the isomer, the word is coined by the year 1830 by Jacob Berzelius. So isomerism is coming from the Greek word. Is iso means equal or same, mer is a parts, so isomers is called as equal parts. So the isomerism means the compound with same chemical formula but different chemical structures. Chemical structure of the atom are called as isomerisms. So that isomers can exhibit distinct physical and chemical properties even though they have the same number and types of atoms. Now we can see about that types of isomerism. So mainly two types of isomerism. Structural isomerism and stereoisomerism. So structural isomerism again divided into first one ionization isomerism, hydrate isomerism, linkage isomerism and coordination isomerism. So structural isomerism again divided into four types: ionization, hydrate, linkage and coordination. So stereoisomerism again divided into two types. One is geometrical isomerism or otherwise is called as cis-trans isomerism, and second one optical isomerism. So this is a main type of isomerism in transition metal compound. It's a two type: structural isomerism and stereoisomerism. So structural isomerism are four types: ionization, hydrate, linkage, coordination. And stereoisomerism are two types: geometrical or cis-trans isomerism, and second one is optical isomerism. So now we learn about the structural isomerism. So structural isomerism, they have same chemical formula and different structural arrangement of atoms are called as structural isomerism. So first we see that ionization isomerism. So ionization isomerism, example, we take that coordination isomer. So we take this coordination isomer, dissolve with water, So this SO4 is called as counter ion and Br is called as a ligand. So we are taking one of the example for coordination ionization isomerism. Dissolved with water, we can get that sulfate ion. So now I interchange the counter ion and ligand. So now bromide is a counter ion and SO4 is the ligand. Now I interchange both counter ion and ligand and dissolve with water. We can get SO4, sorry, Br minus bromide ion. So here the sulfate ion is formed, here bromide ion is formed. So this is an example for ionization isomerism. So the ionization isomerism, the compound with the same molecular formula but give different ion in solution on ionization. So that is for sulfate ion and this is a bromide ion. So same chemical formula but give different ions in solution on ionization. So that is called as an ionization isomerism. So next one, hydrate isomerism. Second one, hydrate isomerism. So let us consider the complex. It contains here 3 isomers. There are 3 isomers are possible in this complex. So there are 3 possible isomers are possible in this complex, and the first one is violet in color, and the second one is grey green in color, and the third isomer is green in color. So now we will see, so here in this complex containing 6 water molecules, here 5 water molecules, here 4 water molecules. So different number of water molecules. So each complex contains a different number of water molecules in the coordination sphere is called as hydrate isomerism. Further we are taking this complex. So this complex is containing 3 different possible isomers are formed. So different number of water molecules combined for each complex, each isomers. So what is hydrate isomerism? It is defined as different position of water molecules both inside and outside of the coordination sphere is called as coordination isomerism. So the isomers are arises due to the difference in the position of water molecule inside and outside of the coordination sphere are called as hydrate isomerism. And third one, linkage isomerism. So before going to the linkage isomerism, we know about that ambidextrous ligand. So what is ambidentate ligand? Taking that example, NO2. So what is the basic concept of the ambidentate ligand? Ligand that can attack through two different atoms. So here nitrogen atom is attacked, here oxygen atom is attacked. The nitrogen atom is attacked is called as nitro N and oxygen atom is attacked is called as nitro O. So similarly, another example, thiocyanate. Another example for ambidentate ligand, thiosulfur is attacked. Another one, so nitrogen is attacked. So one atom is nitrogen, another atom is sulfur. So thiocyanate. So thiocyanate, yes, this is isothiocyanate. N. So that is called as ambidentate ligand. Ligand that can attack either through the two different atoms. Here for NO2 is one of the example for ambidentate ligand and SCN is another example for ambidentate ligand. So now we are coming for that linkage isomerism. Example for linkage isomerism. So this is an example for linkage isomerism. Either the oxygen atom is attached or nitrogen atom is attached. So that is called as a linkage isomerism. So what is linkage isomerism? The definition of linkage isomerism: when the ligands coordinate with the central metal ion through any one of the two atoms. So the ligand attached to central metal, here central metal is a cobalt, and attach any one of the two atoms, either nitrogen atom or oxygen atom or sulfur atom or nitrogen atom. So that is called as nitro N or oxygen nitro O, sulfur thiocyanate S, nitrogen means isothiocyanate N. So for that SCN, another example. So here the nitrogen atom is attached, here sulfur atom is attached. So the nitrogen atom is attached is called as isothiocyanate N and sulfur atom is attached means is called as thiocyanate S. So this is called as a linkage isomerism. So before go for the linkage isomerism, we know about that basic concept of ambidentate ligand. So this is an example for ambidentate ligand NO2, either nitrogen is attacked or oxygen atom is attacked. And thiocyanate, whether the sulfur atom is attached or nitrogen atom is attached. So then only we know about the linkage isomerism. So next one is coordination isomerism. The fourth one, coordination isomerism. So the coordination isomerism, the easy trick is we are coming the two brackets. So that is an easy trick for this coordination isomerism, coming in the two brackets. So take the two coordination compounds. So here zinc is that metal ion, this metal atom, and here copper is that metal atom. So the metal swapping is occur is called as coordination isomerism. So metal swapping occur means here is coming copper and here is coming zinc. So swapping of metal ion between the two coordination compound is called as coordination isomerism. Sometimes the ligand swapping is also occur. So the example for ligand swapping, either metal swapping or ligand swapping. So this is an example for metal swapping. Another example, so this is example for ligand swapping. So this is ammonia and this is for isocyanate. So swapping of ligands. So thiocyanate. So coordination isomerism is a swapping, any swapping is occur. Is a metal swapping or ligand swapping. This is example for coordination isomerism. That's why we are telling. So it's coming for easy trip is coming for the two brackets. So that is called as a coordination isomerism. So that is defined as the isomers formed by switching over or swapping of the metal atom between the two complex ions. So swapping of metal ion or swapping of ligand between the two coordination sphere is called as a coordination isomerism. So far is all of you listen, all of you clear I think. So what is structural isomerism? So structural isomerism, so same molecular formula but different structural arrangement. So that is called four type. First one is ionization isomerism, second one hydrate isomerism, third one linkage isomerism, and fourth one is coordination isomerism. So now coming for that stereo isomerism. So stereo isomerism are two type. So what are the two type of stereo isomerism? So first one is called as geometrical or cis trans isomerism. Stereo isomerism. So stereo isomerism are two type. Geometrical and optical isomerism. So geometrical isomerism are called as cis trans isomerisms. So what is geometrical isomerism or cis trans isomerism? So in this video guys we learn about stereoisomerism. So stereoisomerism are same molecular formula, same structural formula but different spatial arrangement. So there are two types, geometrical and optical isomerism. So geometrical or otherwise called as cis trans isomerism. So now we take an example for cis trans isomerism. So platinum is a central metal. There are two ligands, chloride and ammonia. So this is called as cis isomers. So the same ligand is arranged adjacent to one another, chloride ligand, ammonia ligand. So that is called as a cis isomers. Here, that ammonia ion and chloride ion is opposite to one another. It is called as a trans isomers. So this is called as geometrical isomerism or cis-trans isomerism. So geometrical or cis-trans isomerism, arrangement of ligands. So the ligands are arranged on the same side is called as cis, and the ligands are arranged in the opposite side is called as a trans isomers. And the next one is an optical isomerism. So the finally optical isomerism, same molecular formula, same structural formula, but different behavior towards the light is called as optical isomerism. So in optical isomerism, we are telling about optical activity and non-superimposable. So all of you know about the mirror image. So this is the mirror, and this is the object, and what the mirror image of this object is the image. So that is called as enantiomers. So the example for that optical activity so it's reading ammonia, nitro, bromide and chloride. So how is arrangement? Reading chloride, iodide, ammonia, NO2 and bromide. So this is called as dextro-rotatory, is a positive charge, and mirror image, so it's a mirror, and the image for that one. So bromide, iodide, and the mirror image. So pyridine and chlorine is coming this side, pyridine and chloride is coming this side, and NO2 and ammonia is coming this side. This called as levo-rotatory is a negative side. So dextro-rotatory, levo-rotatory. So dextro-rotatory means is a clockwise rotation, and levo-rotatory means is called as anti-clockwise rotation. So the optical activity is one of the type of stereoisomerism. They have the ability to rotate that PPN. So what is PPN? Is plane polarized light. So the detection and measurement of the optical activity is called as polarimeter. So now we will see the polarimeter for detect the optical activity. So first we can take the source of light. There is a light source. So for taking the light source or the light, we can take the vibration in all directions. So vibration at many different ways. Vibration takes place in many different ways. But it goes to this, the light is passed into the prism. It's a nickel prism or lens. Then we can get PPL. So what is PPL? It's a plane polarized light. So the plane polarized light, vibration takes place only at one particular plane. So vibration in one plane, one particular plane is called as a VPN, that is called as plane polarized light. So you can get that sample solution. So rotate the PPL, rotate the plane polarized light. So this is an observer. So you have to observe it. So rotate the PPL. So we can get any one direction, either clockwise direction or anti-clockwise direction. So clockwise direction is called as, so any one direction, this is called as a polarimeter. So polarimeter means, what is a polarimeter? You have to measure the optical activity of the compound, whether it's a clockwise, rotating clockwise or rotating anti-clockwise. So rotating clockwise means is called as dextro-rotatory, is called as a positive charge, whereas a rotating anti-clockwise is a left side means is called as levo-rotated, that is for negative side. So polarimeter, you can get the light source, ordinary light source, the vibration taking place in many different planes. But it passes through the prism, nickel prism, we can get PPL. So PPL means plane polarized light. So what is plane polarized light? The vibration takes place at only one particular plane. So we can take the sample solution. So rotate the PPL, plane polarized light, any one of the direction. So rotating either clockwise rotation or anti-clockwise rotation. So clockwise rotation are right side or anti-clockwise rotation is the left side. So right side rotation means is called as the dextro-rotatory. Anti-clockwise direction means is the levo-rotatory. That is called as the negative side. That now observe through the PPL whether it's the clockwise rotation or anti-clockwise rotation. So that is called as optical isomerism. So far in this video we discussed about that isomerism in transition metal compounds. So isomerism in transition metal compounds is mainly a two type, structural isomerism and stereoisomerism. So structural isomerism are four type: ionization isomerism, linkage isomerism, hydrate isomerism, coordination isomerism. Whereas the stereoisomerism are two type: geometrical or otherwise is called as cis-trans isomerism, and the last one is called as optical isomerism. So that are the main type of isomerism in transition metal compounds. Thank you guys. So the example for optical isomerism, you can see that another example for optical isomerism. So the optical isomerism is also called as D and L isomers. So D and L isomer is a D stands for dextro and L stands for levo. So all of you know I think is a D is a positive charge and L is a negative charge. So the D is positive means is clockwise direction. It's a clockwise direction means is a right side. L is a negative charge. It's an anti-clockwise direction or left side. So take that example for D and L isomers. The oxalate group is attached here. So 3 oxalate group is attached. So it is called as tri-oxalato. So chromate 3 ion. So center is a chromate ion is the chromium ion. So 3 oxalate group. So tri-oxalato chromate 3 ion. So for D and L isomers, So this is for that example for optical isomers, trioxylato, chromate 3 ion. So oxalate group, 3 oxalate, and the chromate is a center ion. So optical isomers are those two compounds with the same chemical formula, trioxylato chromate 3 ion, such that the mirror image are not superimposable to each other. So this is the mirror image. So not superimposable to each other is called as optical activity. So depending upon the direction, they rotate the PPL. So PPL means it's a plane polarized light. In a polarimeter, we have the two form of optical isomers. So one is called as dextrorotatory, another one is called as levorotatory. Okay.
So chronic gas in this pretty clear about HCA. So HCA is a concept. Because extending already you are studying for AB. So AB is what is acid and basis fixed and AB. So AB is called as acid and basis. But acid and basis are explored. So many concepts. Lease concept, non-lease concept, lease concept, and HSCD concept. So HSCD concept is called as a PFC concept. So the HSCD concept is hard and soft acid and bases. So the student was looking for acid and bases, but now coming for the college students, we are speaking about HSCD hard and soft acid and bases. So each concept has its application. So it's a concept of that this is good, allowing concept is coming after the next concept is coming, and finally the HSCD concept is coming. So having each concept has a big indication and classification of HSCD. So HSCD is mainly that HSCD are based on concept. HSCD is a classified based on bonding of metal ion and ion, that is hard and soft acid base and acid base. Hard acid, hard base, and soft acid and soft base. What is the main application of HCD is widely used in chemistry for explaining the stability of compound and reaction mechanism and pathways. So that is the basic uses of HCD is used in chemistry for explaining the stability of compound, reaction mechanism and pathways. Next we want to discuss about HCD concept. HCD concept or PSN concept. So PSN is the name of the scientist. So HSCD concept or PSN concept. This is unpolarized atom. Of the applied electric field external force. Applied external field. The deformation is taking place. Is called as polarized. It's a polarized atom. Positive charge and this is a negative charge. So that HSCD is explained, the basic concept is explained based on polarization, whether the polarization takes place or not. So this is for unpolarized atom. When the external field, electric field is applied, we can get polarization taking place. That is that the negative ion is towards the positive ion is attracted. So positive and negative attraction taking place. So deformation is taking place. Deform. So the deformation taking place is called as a soft. Whether the deformation does not take place means the deformation does not take place. So does not occur means is called as a card. So what is card itself? We are very so far as read as a basis. So what is card itself? Whether the deformation takes place, whether the polarization takes place or not. So polarization takes place means the diagram is called as a star. Whether the polarization does not take place means the diagram is called as a card. So the card means not strong. So the card itself is explained based on polarization. Whether the polarization takes place or not. So polarization means deformation taking place. Charge moves towards a positive charge. So the deformation is taking place. The bending is occur. So because the ions are moved toward the negative ions move towards a positive ion, so deformation takes place. So deformation takes place means the atom is called as a sound. So deformation does not take place means the atom is called as a hard. So this is called as concept of HSAB or Pearson. So next one, HSAB principle. So according to the HSAB concept, when the HA prefer binding with HB to give the ionic complex, whereas SA prefer binding with SB to give coordinate complex. That is HA prefer binding with HB, whereas SB prefer binding with SA is prefer binding. Here do not prefer binding. This is prefer binding. And here do not prefer binding. This is for the HSAB principle. HA binding with HB and SA binding with HB. So binding takes place only HA, HB, SA and SB. So hard and soft do not before binding. Similarly, soft and hard do not before binding. So HA plus HB, HA plus HB to form a stable compound. So SA plus SB to form a stable compound. So HA plus SB is unstable. Similarly, SA plus HB is unstable. So this is the basic principle of HSAB. So HA bond will take place, SA, SB bond will take place. So hard and soft and hard does not form the bond, it's an unstable compound. So this is the basic principle of HSAB. So so far we have studied about that HSAB concept, or otherwise is called as a Pearson concept. So HSAB concept or Pearson concept we are studying about hard and soft. Hard acid, hard base, soft acid, soft base. So hard and soft is explained based on polarization of atoms, whether the polarization takes place or not. So polarization takes place now, that atom is called as soft. Polarization does not take place now, that atom is called as a hard. What is polarization? On applying the electric field, external field, the negative ion is passing towards the positive ion. So negative positive attraction is taking place. So deformation is taking place. So that is called as a polarization. So the polarization takes place means that atom is called as a soft. Polarization does not take place now, that atom is called as a hard. So that is a basic concept of HSAB, and also basic principle of HSAB. HA prefer binding with HB, SA prefer binding with HB, not hard and soft, not soft and hard.